Hello everyone, my name is Alla and today I'm going to tell you, I'm working at YerevaNN and today I'm going to talk about data specialization, and the title of my speech is Less is More, Data Specialization for Various Modalities. Let's start with the motivation. So what the data specialization is, its goal is to reducing dataset size to improve model quality under a compute-controlled setting. Traditionally, in the era of big data, people think that more data, big models are the solution to get good models or the best with the best performances, but is that always true? Do always big data always good for our models? In large language model processing, people already used to use data curation algorithms to get better results for the models. And only recently, with the Dino version 2 models, they started in the computer vision field. People started to talk about the data curation in the vision field. In this work, our goal is to work with different modalities, not only natural imaging, but the other ones. Let's iterate on this type of data. So natural imaging, it's known with its balanced classes, object-centered images. Also in the natural imaging, you can see vertical-oriented spatial orientation for the objects. The second modality is remote sensing. Remote sensing is imagery is the satellite imagery or aerial one. Here we can use a remote sensing dataset for land cover mapping, and classification, or disaster monitoring, etc. So what are the problems with the remote sensing data? It's like for every remote sensing data have large scales, multi-resolution, so it also differs from when we are considering different satellites. Often multispectral, hyperspectral images, and the main complexity of these images that they aren't centered or clearly defined. And the next one is the X-ray scans. Here are the examples of the images that we are working with. You can use this data to classify different diseases like pneumonia, fibrosis, etc. And these images also have they are very similar in the context of they are very similar. So this data has hit problems within it. And the last one is cell painting and bright field images. Problem here is that images have very high resolution 6-channel images and very different environments in which they are trying to capture different cell images, and also the dataset size can vary up to 100 million data. So let's move to our problem setup. As I said, we are considering here different modalities of the data sets, and the main case here is that our data is big. Also, it has a lot of repetitions and duplicates with the similarity metric, and there is very little diversity in the data set. Also, we are setting up compute constraints. We are fixing our compute and trying in this constraint to maximize chosen metric. For this case, we chose accuracy of KNN using on our trained models, model embeddings. So one of the hypotheses that we have, it's like even if we relax the compute constraints and trying to levitate with different ones, the optimal subset often yields better performance in comparison to using full dataset. In 2024, researchers from Carnegie Mellon University started an experiment for scaling laws for data filtering. They choose different subsets of the data by evaluating it with the predefined chosen metric, and then created different pools for different subsets of the data. E subset is here the most high quality data, and when we're going down to the F, the quality of the dataset is going down. So they are choosing different pools, like combination of different data subsets. And then they show that there is the data curation cannot be agnostic. So when you have a small, when you are filtering your data very aggressively, a lot of repetitions can bring to the drop of the accuracy compared with the large compute and less aggressive filtering filtering dataset training models. So the one case is what we can say here, that for each data subset, compute should be carefully chosen. Also, recently in the field, in the space of X or Twitter, there was some kind of talks about highest, that if you are leaving only high quality data in your pre-training model, and you are also going to very long iterations, the accuracy or metric in which you are checking your model goes down, and in our work we don't so our results differ. So we show here that if you have not that good data initially and have a lot of repetitions in the data like we have here, dropping even 98% of your data can bring to the performance gaining on your data. We can see here for the orange one that our data, for the small subset of carefully chosen data set, it outperforms to the full data set training, even for the 400 million iterations. So in that case, we don't see that full data exists to beat the small subset training data. So let's move to the experimental setup here. We used different pre-trained data sets. One of them is MillionAid. It has 20 million images. It's well curated data. The second one is Maxar imagery, which has 51 images itself, and it has a lot of duplications, repetition within it. The next one is ImageNet 1K. I think that everyone knows it. And the X-ray scans, it's a little one, and it has 340,000 images within it. Everything here we are doing with self-supervised way. Our model is iBot, self-supervised VIT. And also we pre-trained on original data, SAM data filter data, and hierarchical sampling filter data. Every experiment is held on 50 million iterations, and with the same setup of for all data sets. Let's move on the filtering methods. For both algorithms, we calculate Dyna version 2 features for both for all data sets. SAM-dedup, both filtering methods are from Meta AI. SAM-dedup, it's apply k-means on these features and then remove semantic duplicates. And hierarchical sampling does 4-level hierarchical k-means. And then it starts to sample uniformly across the clusters. Evaluation details. We evaluated our work on KNN classification. For ImageNet, we used 75 corrupted types of original validation set and the original validation set itself. For the remote sensing data, we used 3 SAM classification datasets. These are UC Merced, RESISC 45, and Eurosat, and 3 classification datasets for X-ray. Also, for adding some statistics, we used bootstrapping and seed averaging. So let's move on to the results. As I said, MillionAid is well-curated data, and when we are trying to subsample from MillionAid with hierarchical sampling, it's the first one, we see that until 50 million iterations, full dataset outperforms to 1.5 million sample data, but at the end they are starting to be comparable with each other. Also, here we show that SAM-dedup actually doesn't work well, and we are starting to use only hierarchical sampling. This thing we also show with the Maxar1. Here we show also that when we are trying to drop some parts of the data set from our initial one, we show that only for the 1.5 million data, our result is comparable with the last one. For the Maxar itself has a lot of repetitions. It has duplicates because it's like satellite photos taken from different years, but for the same locations. We show here that when we are trying to drop different subsets of our initial data, the maximum evaluation metric we gain with the model trained on 750,000 image samples. Also, we show here that if we go further till the 400 million iterations, our model still outperforms the data set pre-trained with the full data. So the next one is ImageNet evaluations. Here we show that for the well-curated data, sampling algorithms can hurt the model pre-training. Also about the I wanted to talk about a little about that not every data filtering techniques work well with different modalities. We show with X-ray data that our filtering algorithm doesn't work well. And also recently in ICML, one of the ICML publications, we show that for cell microscopy images, also well-known techniques doesn't work. And in this way, one should find out how to curate their data in field-specific, contextual, in field-specific ways. Like they solve that problem with removing like images where images are out of the focus or contain some anomalies or like some kind of dead cell within it. Also, they have different, no information about the data, how they gain it, and also use different, and they're trying to reduce also some different uncertain samples. And in this way, they show that their model with the data less than 5 times outperforms the others. This is the filtered one. And that's why one should choose carefully how to filter their data and also look into the information that they have about the field. So to sum up, as I say, more data isn't always better. We have to choose carefully what subset of data we should use for the pre-trainings. And also effectiveness of filtering algorithm depends on the modality itself. And in a lot of cases, compute also matters, and one should choose also very carefully what, how much you should train your model for getting better results. Thank you for your attention. Now I think we have some time for question answering.
Ask the first question. On this biological data set, can you go back to the results?
This one?
Okay, maybe one more bit before, because so this filtering is more about quality, right? Not about distribution or balance. Is that the case?
Yes, it's more about the quality.
I see. So this is in a way similar to what I was showing before. So if you remove low quality data, that's how you get improvement. Interesting. But then the low quality here is very domain specific. That's the difference.
Yes, because the models cannot understand how to, our models like Dino version 2 that was trained on natural images doesn't understand how to choose which data here is more accurate or for more, has high quality compared with the others. That's why it's nothing work here with this type of the images. I think the main ways that we can continue our research is like finding the automated ways to work with this type of data, because they are very similar with each others, but also they are very different in the way of biology.
Can you go to ImageNet slide? So here we take 100% is full ImageNet, and this is half of the ImageNet filtered by the same algorithm.
Yes.
Before. And then the performance on ImageNet and on ImageNet corrupted is getting slightly worse.
only for the corrupted one, the 50% was slightly higher than 75%. It's like very slightly little.
Okay, do we have more questions?
So, we want to touch on, we're talking about the compute metrics, and then there was this tweet from, I don't remember who was saying that, hey, we were throwing away the bad quality samples, and then it was actually worse. So, if you have a case where you sampled somehow smartly and you got better results, are there any theoretical, I don't want to say guarantees, but can you say that there is some way to throw in whole the data and still get the same results like you would get with curated set?
Like dropping all the data?
So maybe you are, let's say you continue training, simple example at the risk of sounding stupid. You have carefully selected a subset, high quality data, and for a given fixed amount of compute, you have a better model than if you would have thrown all your data in.
Mm-hmm.
But then maybe if you kept training your model or like did slightly differently, but more, basically throwing in more compute on the whole data, you would achieve at least the same quality of the model as with your curated set and less compute.
I think it's more about the scaling laws, like scaling laws that we decided to do. Yes, it can be true, but we will show how it can be shown mathematically.
Go the other slide, the next slide, one more, your first, and this one.
Uh-huh.
Does this answer your question?
I'm not sure.
Look, this is training amount, and the colors are data size. So the orange one is full, and imagine my compute budget was this much.
No, they're right, but you don't know what happens later. Maybe you would have trained differently, so maybe with a different algorithm, and then maybe there is a smart theorem somewhere in a...
It's about scaling laws. We wanted to, let's say we have different computes like 10 millions, 20, 30, 50 millions iterations done with the different subsets, full or subsets. We want to get some scaling law, how we can extrapolate this dependency to this one. So I can calculate some metrics and say that in 400 iterations, with the high probability, the performance of my model will be like this in this point. There is no theoretic results for this in image computer vision, but one of our goals is to get that mathematical expression that can answer your question. So with the little experiments on short trainings, how can I predict how my performance of my model can get better? So it's one of our questions, our main questions that we are still studying.
On Newton's papers, they show that if you have enough compute, you can...
Yeah, here they show it. These points are predicted ones.
So actually it's different people, you said
Yeah.
different data. Lion, different training,
But also difference here from our models, it's that measuring of the quality of the data and filtering algorithms aren't self-supervised. They are supervised, and it's kind of act in different ways when you are training models.
Thank you for the talk. I was wondering whether you have any insights about the shuffling data within this good sample of that you created. So let me elaborate. So let's say you take the good sample, you understand that this small data training gives a good result, but within this small data, maybe you have like good examples and
We didn't do something like that because our metric doesn't allow us to find out what images are hard ones and what are the easy ones, because we don't have any, we are assuming that we don't have any labels on our data. But about the shuffling, I'm not sure that I can answer on that question, because if we have like already defined subset, we trained our model like 5 times on the same subset with different seeds, so we can shuffle it within each other. And here we can see the error of our models. It's like very close to each other. So I don't think that the shuffling helps here, and it can help. I don't know.
More questions?
Thank you for your presentation. I'm curious, what was your strategy on removing your datasets? I noticed that you removed out of focus images, so I mean the images with bad quality. But regarding images with, for example, with dieses or without dieses, have you applied a more sophisticated selection of this subset of your data? And this is one question, and another, the second related question. Have you watched on false positive rate while you're decreasing your subset? So I mean, if, in my opinion, if we reduce our data set, we can face with, grow up with all false positive cases. Please.
I'll start with the second one. No, we didn't calculate any precision or recall. We just calculated accuracy within different downstream tasks, and then just averaging through the averaging within these that downstream tasks. And for the first question, this type of filtering we didn't do. This is from the vitally consistent scaling biology presentation learning for cell microscopy. It's from the other different paper with different authors. It was published in ICML in this year. For the chest one, we just try to use our SEM-dedupe and hierarchical clustering algorithm, and then we show that that type of algorithm doesn't work. So we have to find what type of filtering algorithms we can implement for that type of data. So maybe we can, maybe different like pixel level or different algorithms can work here much better. Any more questions?
More questions? We can thank Alla again.
Thank you very much.